Okay. So now let's talk about reaction mechanisms. We said that one of the reasons we were interested in doing and studying rates of reactions is it gives us insight into what's going on at the molecular level. Okay, so a reaction mechanism, we're really interested in what must be going on during a chemical reaction, because if you understand how the molecules are behaving, then that gives you power. It gives you power to manipulate the molecules so they do what you want them to do, right? So let's talk about reaction mechanisms then. In this lesson, you're going to be able to define what a reaction mechanism is, what elementary and complex reactions are, and what molecularity means. Given a mechanism, you need to be able to identify the reaction, what's called the reaction intermediate, and catalysts, and you need to be able to relate the rate law to the reaction mechanism. So given some simple mechanisms, I would expect you to be able to predict what the rate law is. In other words, what we're trying to say is if you're going to propose a mechanism for a reaction, a mechanism is really something you just propose. You make an intelligent guess as to what it would be based on observations, including rates. Okay, so whatever mechanism you propose, it's not really something you can prove. Okay, but for it to be acceptable, it has to be consistent with the observed rate law. So your mechanism for your mechanism to be acceptable, okay, at least it should make a prediction that is consistent with what is observed as the rate law for the reaction. Okay, so what's a reaction mechanism? It's just a series of steps of molecular events, so things happening at the molecular level that will explain how your reactant molecules are converted into product molecules. Okay, and like I said, it has to be consistent with the experimentally observed rate law. So we can, in other words, we can experimentally obtain evidence to support our mechanism. Okay, but we cannot prove a mechanism. Okay, all it takes is one experimental information that's inconsistent with what mechanism we're proposing, and we have to throw it out or modify it. So it's easy. You can disprove a mechanism. But what you do is you collect a whole bunch of experimental observation, and so come up with a mechanism that's consistent with a lot of experimental observation that will give you a lot of confidence in your proposed mechanism. Each step in your mechanism, each molecular event is called an elementary reaction or an elementary step. And most reactions, typically reactions are multi-step or complex reactions. They actually involve more than one elementary reaction, more than one molecular event. Okay? So, for each elementary step, okay, we can trace what happens to the potential energy as the atoms of the molecules move. Okay, they move towards each other and move away from each other. So bonds get broken, bonds get formed. We can trace the potential energy, and typically what happens is, as the reaction progresses, this is called the reaction coordinate. That's just our generic way of representing what's the progress of the reaction. Okay, so the changes in the relative locations of your atoms. Okay, as the reaction progresses, typically your potential energy is going to rise. Okay, it reaches at the highest point. You have what is called a transition state. Okay, and then it drops. It may drop below the original potential energy. In that case, you have what's called an exothermic reaction. This delta H here is going to be a negative number. Or it's also possible, okay, that it would fall to a higher level compared to the original potential energy. And so this delta H here would be positive, and you would have an endothermic step. Okay, so this illustration right here would be an endothermic. If I were to do something like this, that would be an exothermic step. Okay, so this is what we call the potential energy profile for an elementary step. Okay, it goes through maximum and then it goes back down. So the minimum energy that your reactants need to be able to get to the transition state is called your energy of activation. Okay? Now, because reactions happen as a result of collisions, it's possible for your product molecules to get together and get back and form the reactants, right? So your products, imagine the reaction going in reverse, okay? Then if the reaction goes back, the products go back to your transition state, the minimum energy they need, that would be the energy of activation for the reverse process, okay? So typically, a mechanism will involve a transition state where your reactant bonds are partially broken and product bonds are partially formed. The energy of activation, okay, the energy of activation that we have here, which we are showing here, will typically be less than the energy needed to break the bonds, okay, because while you're forming your transition state, as your atoms change their positions relative to each other, there could you could be changing the potential energy of the entire system. So what you would normally need to break a bond, that energy might be more than you'd have. Let's see, you'd require less, okay, to get to the transition state than the energy just to break that bond, okay. So if you need to break the bond, you might need way more energy, but because of the way the atoms are aligned, okay, are oriented relative to each other, you can get to the transition state with less energy. And so that amount of energy is called your activation energy. All right, so true or false? Let's look at this clicker question here. Which of this is true about reaction mechanisms and experimental data? A, experimental data can disprove a proposed mechanism. B, experimental data can prove a proposed mechanism. Or C, neither. All right. So what did we say about mechanisms? You can never prove them, right? But it takes one piece of information that's inconsistent with your mechanism to disprove it. Very good. Consider the reaction. H2 plus I2 gas gives you 2HI gas. True or false? Without any experimental data, we can say for sure that the reaction is elementary. The answer is false. What did I just say about reaction mechanisms? It has to be an educated guess, right, about what's going on. You have to base it on some kind of information. Regardless of how simple a reaction looks, you cannot say right away that you're dealing with an elementary reaction. Okay. In fact, this particular reaction is not a one-step reaction. Most reactions are typically multi-step. So several things could happen before this transformation can actually occur. Okay, so this is false. Right. The only way to really know, you really have no way to know, there's no way for you to know for sure. Okay, here's the thing that makes this really false. You cannot for sure say that a reaction is elementary. You can only propose that it's elementary. So you can say, based on all of this experimental observation, I would propose that this is what happened, this step happened, and then this step happened, and then this step happened. So you can propose elementary reactions, but you cannot for sure say that just given a reaction that is an elementary reaction. Okay? How about this one? If you have a mechanism that looks like, where the potential energy looks like this versus reaction coordinates, so you're going from reactant to product, okay? How many steps are involved in the mechanism that's associated with, so if you propose a mechanism that's where the potential energy profile looks like this, how many steps are involved in that mechanism? 1, 2, or 3? Okay, answer is 2. Okay, so This would be the first step. So this thing right here would be the transition state for the first step, right? And then yeah, what you form during that first step is what you would call an intermediate, a reaction intermediate. And then there's a second step here. Your second step goes from the intermediate, transforms your intermediate to product. Okay, and so you have another transition state here. That would be for your second step. So that's 2 elementary steps. So typically, for each elementary step, you have a hump. You have a transition state. Okay? Molecularity. The word molecularity refers to the number of molecules that are involved in an elementary reaction. Okay? What's an elementary reaction? An actual molecular event, right? So a unimolecular reaction, okay, an elementary reaction that has a molecularity of 1, okay, so molecularity of 1 is called a unimolecular process. That involves simply a molecule that fragments, falls apart. So it involves just one molecule falling apart into 2 pieces, 2 or more pieces, or one molecule rearranging its the way rearranging the atoms within the molecule. Okay. Now, if you have a collision of 2 molecules, then you say the molecularity is 2. So the process we call that a bimolecular process. If you have 3 molecules involved, 3 molecules colliding, then that's a termolecular, as in ternary, tertiary, number 3, or trimolecular. Okay? Now, molecularity is greater than 2. Any step that involves a collision of more than 2 molecules are very unlikely. So when you propose mechanisms, you generally propose mechanisms that steps that involve only 1 or 2 molecules. Okay, so that's what molecularity means. So let's consider the hypothetical elementary reaction. We have A plus A yields B. So would you call this elementary reactions? I'm telling you that I'm proposing this to be an elementary reaction. Is this reaction considered unimolecular, bimolecular, or termolecular? That's 2 molecules of A colliding, getting stuck together, and the pair that's stuck together, we call that B. No trick here. Bimolecular. 2 molecules colliding, okay? And usually it's a giveaway that it's bimolecular, especially if it's written this way, because otherwise you would just say 2A yields. Usually when you write mechanisms, when you propose elementary steps, if you're to emphasize that it is a bimolecular process, even though you could have abbreviated this as 2A, you would write it as A plus A gives B, okay? So the number of molecules that's actually involved, if I tell you, it's called, will be the molecularity, even if they're the same kind. Okay, so the fact that I call this an elementary reaction, that means I'm telling you, I'm proposing that in this particular case, 2 molecules of A collide to give you a molecule of B. Okay, so that's a bimolecular step, a bimolecular reaction. Now, how is molecularity related to the reaction order? The reaction order of an elementary reaction is equal to the molecularity. So for example, if I say that this reaction right here is unimolecular, then if I propose that to be a unimolecular, an elementary reaction, then I would expect, if I were to go to the lab and made measurements, I would expect to find the rate law to be equal to K times the concentration of A. Rate equals K times concentration of A. It's going to be first order. So if the molecularity is 1, okay, then the rate law would be first order. If the molecularity is 2, what would be the overall order for the rate law? It's going to be second order. So for example, if I have 2 molecules of A colliding to form B, then the rate law would be rate equals K times A squared. It's K times concentration of A times concentration of A. If it's termolecular, And this one, there's another bimolecular. If it's a bimolecular reaction that involves a collision of A and B, then I would expect the rate law to be rate equals K times concentration of A times concentration of B. Okay, so this is also, so this bimolecular reaction right here, okay, so this bimolecular reaction has a second order rate law. Why is this second order overall? Because it's first order with respect to A and first order with respect to B. So overall, it's second order. Okay? So if you know the molecularity, then you should know what the reaction or experimental order of reaction is. Okay? Now, but, there's a big but here. Your reaction order is experimentally determined always. Okay? You can predict what it would be if you propose a mechanism. But the only way to know for sure what the rate law is you actually do it in the lab. And we talked about that in the last lesson, right? So it doesn't mean that if you find something that is second order in the lab that the mechanism, it's an elementary step and it's bimolecular. It doesn't, the reverse conclusion doesn't work, okay? Because not every reaction is elementary, remember? So a reaction can be a series of elementary steps, and if you measure the rate law in the lab, it might turn out to be zero order, first order, second order. So the reaction order is really something you only determine in the lab. Okay? Whatever series of elementary steps you propose, it must predict a rate law that's consistent with the observed rate law. So how are we going to do that? In general, like I said, if it's just a one-step reaction, molecularity will tell you what the rate law is. But if it's a series of steps, then there's something else you have to do to figure out, to predict what the rate law is going to be. And whatever prediction you make should be consistent with what you measure in the lab. Okay, so if I say the rate law is second order with respect to A, it doesn't mean that it's an elementary step, that it's a bimolecular reaction. It could be, but it doesn't have to be. So we're going to illustrate that with a few simple mechanisms, okay? But before that, let me just quickly check to make sure you got that. Let's say you have a hypothetical elementary reaction. Collision of two X molecules gives you Y and Z. What is the rate law for this reaction? Okay. So if you know the molecularity, you should be able to say what the order is, right? But if you know what the order is, it doesn't mean that you know what the molecularity is. Okay, not necessarily. So it doesn't go both ways, right? So this one is second order. Second order with respect to X. Okay? How about this one? What is the rate law for this reaction? 2I gives you I2 gas. Okay, you fell for my trick. I did not say that this is elementary. Since I did not tell you it's elementary, you don't have enough information. Okay? You can only predict the rate law given a chemical equation if you're told that that's an elementary reaction. This, in fact, is not an elementary reaction. Bond formation, we talked about this earlier. The correct answer here is C. Remember bond formation, in order for two atoms to get stuck in a bond, when two atoms are about to collide, Okay, when they collide, they're just going to separate and not form a molecule, right? If they have enough energy to be separated to begin with, when they collide, they're not going to form a molecule. The only way they can form a bond if there's a third body that comes along and collides with them and takes that energy away from them. Combination of two atoms to form a diatomic molecule is in fact a third order process. Okay, so it's not, the rate law for this would be something like K times I times the I squared times the concentration of a molecule. That M right there would be total concentration of all the molecules in your system. Okay, so this is not necessarily this is not an elementary reaction. If I told you that I'm proposing this to be an elementary reaction, then you say, yeah, then it would be A. Okay, so be alert to that. If it doesn't say it's an elementary reaction, if it's not obvious that it's an elementary reaction, it's not being proposed as part of a mechanism. So in other words, it's not being proposed as an elementary reaction. Don't assume that it is. Okay, so this one you don't have enough information. How about this one? 2NO2 plus F2 yields 2FNO2. This reaction is most probably A, an elementary reaction, B, a multi-step or complex reaction. All right, so what's the likelihood that you're going to see three molecules colliding? Not very likely, right? So it can happen, but it's not very likely. So most likely this is a multi-step reaction. Okay. So proposing a thermomolecular process as part of a mechanism is generally not a good idea. But if you have enough experimental evidence to say that that's what's going on, sure, no problem. But if you're going to propose mechanisms, chances are your best bet would be to go with a series of either unimolecular or bimolecular steps. So the answer there is most likely that's a multi-step reaction. Okay? So how do you predict what the rate law is going to be given a mechanism for a multi-step reaction? Okay, like I said, your reaction order has to be experimentally determined, but with a proposed mechanism, you can predict what the rate law would be, and so that prediction should be consistent with the experimentally determined rate law. And one thing you realize is when you start proposing mechanisms is that there might be typically there could be more than one mechanism that would be consistent with the rate law. Okay? And that is why you cannot use a rate law to prove a mechanism. You can just say, okay, this mechanism I'm proposing is consistent with that rate law. Somebody else might come up with a different mechanism and say, my mechanism is consistent with that rate law. So the question is which is which. There would be other experiments you'll have to do to determine how, which mechanism is more plausible. Okay? And multi-step reactions also, one thing you'll find is they may not always have simple rate laws. Okay, so you might have fractional orders, you might have the concentration of the reactant in a denominator in your rate law expression. Okay, so let's look at just some simple mechanisms, and let's look at the simplest type is one where you have a series of steps, but the first step is the slowest. So that's your rate determining step. Okay, so for example, this particular reaction here, 2NO2 plus F2 gives you 2FNO2. If you did the experiment for this, you'll find that the rate law is this one. Rate equals K times NO2 times F2. Right away, look at that. Look at that rate law. It's only first order with respect to NO2. Although your coefficient for NO2 in your balance equation is 2. Right there and then that tells you this can't be a one-step mechanism, right? This can't be a one-step reaction. So what kind of mechanism would lead to this type of rate law for this overall reaction that we have here? So here's one possible proposed mechanism. The simplest one you can propose, okay, is one where there's a first step that is very slow compared to all the other steps. So that step you say is your rate determining step. that determines the rate of the reaction. And so the rate law will just reflect the rate law for that particular step. So that's a very simple case. So here you're proposing that NO2, one molecule of NO2 collides with a molecule of F2, and what happens? What happened here? This F2 apparently split up, right? One of the fluorines attaches itself to the NO2, and then that leaves the other fluorine atom. So you have a collision between these two molecules, and we're proposing that that's a slow step. And then we propose in step 2 that this fluorine here, that's produced in step 1, finds another NO2 molecule really fast and gives you the other product, FNO2, another FNO2 molecule, and that's fast. And so step 1, we say, since it's slow, will be your rate determining step. The rate law for the reaction would just say that the rate is equal to the rate of step 1. What's the rate for step 1? It's just K times concentration of NO times concentration of F2. So that's your rate law. That would be consistent. So F here, what do we call F here? It's not a reactant, it's not a product, right? That would be what you would call a reaction intermediate. Okay? So one evidence you might want, one experiment you might want to design in the lab, if you want to further investigate the plausibility of this mechanism, you should go design an experiment that would allow you to detect those fluorine atoms, the reaction intermediate. Okay, so let me give you an analogy for this to make it easier to remember. Let's say the rate at which you produce a hamburger. Okay, so your first step is you put your patty on the grill. Takes a long time to cook that, right? Your second step is you put the patty between a pair of 2 slices of bread, right? Inside your bun. Put the patty in the bun. How long does it take to put a cooked patty in the bun? 2 seconds? How long does it take to grill your meat? Several minutes? 30 minutes? It depends on whether you want it well done or raw or rare. Right? But it takes longer to cook the hamburger, the patty. So step 1 is very slow. Step 2, it doesn't really matter, right? If step 2 is really fast compared to step 2, the rate of your reaction, the rate at which you can sell your hamburger, or the rate at which you can produce your hamburger would be dependent only on how fast you can cook your patty. Okay? So that's a simple case. Let's look at another one. Here's a test yourself question, clicker question. Let's say you have a reaction between carbon monoxide and NO2, and that produces carbon dioxide plus NO. So what happened here? Your oxygen transfers from NO2 to CO, right? And here's the proposed mechanism. NO2 plus NO2 gives you NO3 plus NO. What happened there? One of the oxygens from one of the NO2s transferred to the other NO2, right? So let's say you propose that to be the slow step. And then what happens afterward is your NO3 will collide with carbon monoxide to give you NO2 plus carbon dioxide. So overall, what happened here? If you add up these two reactions, what do you get? Your NO3 cancels out, right? So you have 1. And one of the NO2s cancel out, so you have effectively you're converting NO2 and CO into NO and CO2. Okay, so that's your overall reaction right there. Okay, so here's a mechanism that would lead to the conversion of carbon monoxide and NO2 into carbon dioxide and nitric oxide. So based on this proposed mechanism, which one is a reaction intermediate? Is it carbon monoxide, NO2, NO3, or NO? What's a reaction intermediate? That's something that is formed in one of the steps of your mechanism, but eventually that is converted to products, right? So you don't have any of it at the end. So in other words, if I were to be able to monitor the concentration of a reaction intermediate, what would happen? What would it look like versus time? So concentration of intermediate, what would it look like? I'd start with nothing, right? And have I have something, I'll make some, but what happens when I make it? Eventually it converts to product, so the concentration will rise and then it will go back down, right? And reaction intermediates, typically when you propose those, you might propose something that would be not very stable. It's very reactive. It's very transient. Okay, so typically, if you can monitor that, its concentration is not going to build up too much. Okay, it's going to be very low concentration compared to the amount of reactants and products that's going to be involved in your reaction. So you might have something that looks like this. If your reactant, okay, if your reactant goes from like that, reactant concentration versus time, your intermediate concentration might look something like this. Okay? So the fact that it's not obvious that it's there during your experiment suggests that you're not building up a lot of it. But with very sophisticated instrumentation, you should be able to detect some of these intermediates that you can propose in a mechanism. Okay, there's some more advanced laboratory techniques that you can use to monitor very low concentrations. So what was the answer to this? Did I do a poll on this already? Okay. Popular answer was NO3. Why NO3? You made it in step 1, but you lost it in step 2, and you don't have any of it at the end, right? So that's an intermediate. What would be the potential energy profile for this versus extent of reaction, progress of reaction? What would it look like? It's going to have 2 humps, right? And if this happens to be positive, then that would be that would be an endothermic reaction, right? If it happens to be an exothermic reaction, then you'll have to do this down here, right? You have to have a lower potential energy for the product. Okay, so in an endothermic reaction, the potential energy of the products would be higher than the original reactants. In an exothermic reaction, the potential energy of the products would be lower than the original reactants. So what would you call carbon monoxide here? It's not a reaction intermediate. What would it be? That's a reactant, right? NO2 would be also a reactant, okay? And NO would be a product. What would CO2 be? A product. Okay, so if it's the same reaction, same mechanism proposed in the earlier slide, what would be the experimental rate law that would be consistent with this mechanism? You're proposing that step 1 is slow, step 2 is fast. What would be the rate law for this mechanism that you would observe in the lab if this was the mechanism? Which part of this is the cooking of the patty? Which part is the putting the patty in the bun? Correct answer. Okay. Some disagreement here. I'll give you a little time to talk it over and we'll do another poll. Go ahead. What's the rate law for this reaction? you're trying to determine the rate law, you look at the steps. You don't look at the overall reaction, right? And so, okay, let's do it again. Okay, how do you do it this time? A. Very good. Alright, correct answer is A. Why A? That's your slow step. The rate for step 1, so rate for step 1, and let me call that V1. V1 is K times NO2 squared. What's the rate for step 2? It's K times NO3 times CO, right? But it doesn't matter. Step 2 doesn't matter as far as the overall reaction is concerned because it's very fast compared to step 1. So we say the rate determining step is step 1. It's step 1 that determines what the overall rate of the reaction is. We say that is your rate determining step. So A is the correct answer. Okay. Here's another simple case. Okay. Where you have one slow step, but it's preceded by very fast reversible steps. Okay. So in this particular example, let's look at this reaction of 2NO plus Br2 gives you 2NOBr. Okay. The rate law for this is equal to K times NO squared, okay, times the concentration of bromine. You might say, based on that rate law, it seems like something that would be consistent with that would be one single step where you have two NOs and a Br2 colliding to give you your products, right? One elementary step, two NO molecules involved, a bromine molecules involved, all three molecules collide and they give you a product. That would be consistent with that. But remember what we said? There could be more than one mechanism that would be consistent with an observed rate law. In fact, okay, if you can come up with a mechanism that doesn't involve more than a bimolecular step, if all your steps are either just unimolecular or bimolecular, that might be actually more plausible, as opposed to one where you actually have three colliding right away. So here's a proposed mechanism that might be consistent with that, okay? Like I said, a one-step thermomolecular reaction is certainly consistent with that, but it's not likely. So here's a mechanism that would be consistent with that. So here's your first step. It's fast reversible, so I really should be drawing two arrows there, okay? So in the first step, an NO collides with the Br2, and they get stuck to form NOBr2. And then that's reversible. That means when they get stuck, the NOBr2 could just also split up to give you back NO plus Br2. And then step 2, your NOBr2 collides with another NO and gives you your two NOBrs, which would be your products. Okay, so if you combine these two, what do you see? The overall reaction is NO plus Br2 gives you NOBr2, and NOBr2 plus NO gives you 2NOBr. If you combine these two, what happens? Your NOBr2 cancels out, and your overall reaction has two NOs, right? Plus Br2 yields 2NOBr. Okay? So what's the predicted rate based on this reaction, this mechanism? If this was the mechanism, what would be your rate determining step? Step 1 or step 2? Step 2, the slow step, right? So we say you would expect to observe the rate law to be K2 times concentration of NOBr2 times concentration of NO. All right? Now, that's not what the rate law is. What's our rate law? It's K times rate equals K times NO2 squared, NO squared times Br2. Well, what's the problem with this rate law right here? this NOBR2, we are proposing it as an intermediate. Okay, generally you don't write rate laws in terms of intermediates because intermediates are not something you can easily control in the lab. In fact, they're very hard to measure. But we have, what we did here is we have set up the mechanism so we can express this concentration of the intermediate in terms of things that are easily measured in the lab, like the concentration of reactants and products. So what we're assuming that the first step is fast and reversible, right? So if we're assuming that the first step is fast and reversible, then we say, okay, step 1, forward rate, forward reaction. The rate, so we call that V1, is equal to K times NO times Br2. Okay? The rate law for the forward reaction for step 1 is K times NO times Br2. What's the rate for the reverse reaction for step 1? V sub negative 1, that's usually how we would write it, is equal to some constant K times, what's the reactant for the reverse of step 1? What do we mean by the reverse of step 1? The product is behaving like the reactant and the reactant is behaving like the product, right? So this is your reactant for the reverse of step 1. So it's equal to K times the concentration of NOBr2, okay? And now, the rate constants for forward and reverse reactions are not going to be the same. So to make that distinction, we're going to call this K1 and we're going to call this K sub negative 1. Okay, those are just labels. K1 is the rate constant for step 1 going forward. K sub negative 1, that's the negative 1, that's just a label. That's the rate constant for the reverse of step 1. Okay, so now, we can assume then, we're assuming here that since we're assuming that step 1 is fast and reversible, that means throughout most of the reaction, these two are going at equal rates. In other words, we're going to assume that the forward reaction, okay, V1, is equal to the reverse reaction for step 1. So V1 equals V sub negative 1. Okay, so this is V1 right here, and that's V sub negative 1. Well, if that's the case, what do we get? Let's rewrite that here. We're going to say K1 times NO times Br2 throughout most of the reactions. Got it wrong. I got it written wrong. Okay, here. K1 times NO times Br2. The forward rate for step 1 is equal to the reverse rate. Okay? Is equal to K sub negative 1 times NO Br2. Let's look at this. Well, if I did this, you'll notice that I can solve for NOBr2 in terms of NO and Br2, which are easily measured. Okay? I'm using this equation, I can get an expression for my intermediate, concentration of my intermediate in terms of the concentration of my reactants NO and Br2. How do I solve for the concentration of NOBr2 here? Divide both sides by 1. Divide both sides by K sub negative 1, right? So I can say the concentration of NOBr2 is equal to K1 times NO times Br2 over K sub negative 1. Okay? So I have an expression for NOBr2. I can plug that into my original expression, which was, what was my rate law for my slow step? Let's go back to our slow step, and which is the rate law for my reaction, right? We say that rate is equal to K2, it's right here, times NOBr2 times NO, right? And remember we said we don't like to see this in our rate law because we can't determine that experimentally. But now I have an expression for NOBr2 down here. So this is going to be equal to K2 times, this is the expression for NOBr2. This is going to be times K1 times NO times Br2 over K sub negative 1, and then this one goes down here, that's NO. Okay, so what I've done is I've replaced the concentration of NOBr2 by this expression down here. So how can I simplify this now? I can simplify this to say I'm going to collect all of these constants right here. These are all constants. I can just call them all into a constant times a constant divided by another constant is just another constant. So I'm just going to call it K. And what is NO times NO? NO squared, right? And I have Br2 right here. Right here. So here's a rate law that you can predict from this mechanism right here. So this proposed mechanism right here, we say is going to be consistent with the observed rate law, which is second order with respect to NO and first order with respect to Br2. Okay? So these are just two of the simplest possible types of mechanism that you could propose to explain a reaction. Let's look at this one. Okay, you're going to need time to work this out. You have a fast reversible step again, okay, and your slow step follows that fast reversible step, okay. What experimental rate law would be consistent with this mechanism? What would you predict would be the rate law for this mechanism? What would you have to do? The rate law would be the rate law for which step? Step 2, the slow step, right? So you're going to say your rate is equal to K2, the rate constant for step 2, times NO3 times CO. Okay, do you see any of that here? No. But, okay, let's see if we can make it look like one of these three. NO3, what do you know about NO3? Is that involved as a reactant or a product? Do you see NO3 over here? Overall reaction? No. What do you call NO3? An intermediate, right? So you don't want to see the concentration of an intermediate in your predicted rate law. So you need to express it in terms of the reactants and or products of your reaction. So what do we do here? We'll go back to step 1. What did we say from step 1 is going to involve? If you go back to step 1, you'll find that, okay, we're proposing that it's fast and reversible. So V1 is equal to what? K1 times the forward step, that's going to be NO2 squared, right? What's the rate law for the reverse of step 1? V sub negative 1 equals K sub negative 1 times NO3 times NO. Alright? And what assumption are we making? That because it's fast and reversible, that throughout most of the reaction, this thing, which is V1, is equal to this thing, right? So we say K1 times NO2 squared equals K sub negative 1 times NO3 times NO. And what's my goal for doing this? I want to be able to express NO3 in terms of things that are more easily measured in the lab. So I'm going to say NO3, my intermediate, is equal to what? K1 NO2 squared divided by K sub negative 1 times NO. So I plug that into where? My original expression. So this thing right here. Oh, what did I just do? Ah, let me rewrite this. Is there an undo button here? Oh, let me just rewrite the whole thing. Do over. What was NO3 again? Okay, NO3 right here is K1 NO2 squared over K sub negative 1 NO, right? So I substitute that. This one right here goes for the expression for NO3. So let me rewrite my rate law. It's K2. So my rate, which is going to be equal to V3, is equal to V2 is equal to K2 times NO3, and NO3 is this whole thing right here. K1 NO2 squared over K negative 1 NO. So it's K2 times NO3 times carbon monoxide. So times carbon monoxide. Okay? I'll let you simplify that. Is that correct? NO2 squared over NO, right? Times CO. So, is it A, B, or C? Go ahead and simplify it and tell me what the mechanism is going to be. And what the rate law is going to be based on this mechanism. Is it A, B, or C? Alright, so C. Very good. Alright, so what's the order of the reaction with respect to NO? So say your rate is equal to K NO2 squared, right, times CO over NO. So we say it's second order with respect to NO2. It's first order with respect to CO. What's the order with respect to NO? It's -1. Here you have a special case of a reactant, a product, NO is your product, that slows down your reaction. As you're forming more NO, okay, it's going to slow down the reaction because that denominator is going to get bigger. Okay, so that might be something you'd try to look for in the lab if you're proposing that that's a mechanism. That's some. If this is your mechanism, then this would be the rate law you'll be observing, and that might be the reason you would be led to this proposing this type of mechanism. If you're seeing that the formation of your reactions is being slowed down by the formation of the product. Okay, so you can add NO to your mixture and see how it affects the rate law. Okay. Catalysts. A catalyst speeds up a reaction by providing a different mechanism with a lower energy of activation. We've talked about that already. It's not consumed. It's regenerated at the end of the reaction. So a typical mechanism that involves a catalyst would be a lot of those reactions going on in biological systems, in living systems. They're catalyzed by large molecules, protein molecules called enzymes. Okay, so those enzyme catalyzed reactions. Typical mechanism for those is you have an enzyme. What it does is it binds a substrate. A substrate is the reactant. Okay, so it's a molecule that gets bound to your enzyme, and then by being bound to the enzyme, it undergoes a change, and so when it's transformed into a product, it's released by the enzyme. Okay, so you'll notice in this particular case, okay, your enzyme is bound to the subscript, but then in the end, it's released back. So overall, what's the reaction here? enzyme plus substrate gives you enzyme substrate complex. And then the enzyme substrate complex will give you back the enzyme and a product. So if you add these two, you have that cancels out. So you have substrate turns into product. Okay, your substrate would be your reactant. So that's your overall reaction. Okay. Here's mechanism for the destruction of ozone. Proposed mechanism. You have a molecule collides with an ozone molecule, gives you MO plus O2. Okay. So M here could be any molecule, right? And then you have the MO here collides with an oxygen to give you back O2, to give you O2, and that's a fast step, and it re-releases the M. Okay. So if this was the mechanism, what's your overall reaction? M over M plus O3 gives you MO plus O2, and then MO plus O gives you M plus O2. If I add these two up, what do I get? Your MO cancels out, right? And your M cancels out. So the net reaction that you're getting here is what? O3 plus O gives you two O2s, right? That's your overall reaction. So in this mechanism, what are the reactants? O3 and O, right? Those are your reactants. What is the catalyst? M is a catalyst. What is the product? O2 is your product. What is the reaction intermediate? MO. And what's the rate law? What's the rate law? The rate, what's the rate determining step? The slow step. So the rate law would be equal to will be the rate law for the slow step. So rate is equal to K times M times O3. Okay. What is the overall order of this reaction? Second order. What's the molecularity of the first step? How many molecules are involved in the first step? 2. So the first step is bimolecular. Okay? What's the molecularity of the second step? Also 2, bimolecular. Although you might say that's an atom. When we talk about molecularity, we'll treat an atom as though it's a molecule. Okay? So that's also bimolecular. Okay? And that's it for that lesson.